Thank you. Good afternoon. So indeed, my name is Eric. I am officially a software engineer, but I prefer to think of myself as a geek who likes to use technology to do sometimes useful, sometimes less useful things. I'm not a dinosaur yet, but I've been around for a while, and so I've used quite a few different systems over the years. However, I'm not an embedded system engineer or an electrical engineer. And I discovered really the world of embedded back a few months in April when Apple published a blog post on Swift.org publishing the GitHub repo with the embedded Swift examples. And so this talk is about my journey with embedded Swift, with its ups and downs. But before we dive in, let me just take a moment to further introduce myself. I like running. I started like 10 years ago, no competition or anything, but I like to gather some data to see if I'm improving, help with preventing injuries. And so I measure my heart rate. I have a sensor on my shoe that can measure my stride length and my vertical oscillation and all that kind of things. Also measure my weight. And so after a long data analysis, what I found out is that for a certain fact, I know that if it's cold or if it's raining, I stay at home. And so I have that's a lot of machine learning there. And we built an eco-friendly home, so traditional material like stone, wood, clay, etc. But being a geek, of course, I wanted tech, and so I put a home automation system, whole house audio, and I put sensors everywhere so I can have a dashboard with temperatures in the rooms or the electricity consumption. And we lived there with my wife and son, and when he was a bit younger, I bought some robot kits. And so we had some fun together. I wanted to interest him in technology. He didn't really get hooked, but we spent good time, so that was the most important. Now he's grown up, and he's studying to be a videographer, more specifically a drone videographer. Now, if I'm telling you all this, is not only to plug his Instagram, so check it out, but it is mainly to show you that whatever you do in your everyday life, you will probably be interacting with embedded devices. So really, they are everywhere, those small microcontrollers embedded in dedicated hardware meant for a specific purpose. And so that means there is a lot of code there running on embedded devices. And if you're on fruit diet, same thing, lots of embedded devices. And now if you're a maker, then you know what I'm talking about. They are the small boards, they're cheap, they are a ton of IOs, low power consumption, and you can do a ton of projects with them. So that was for embedded. Now, what about Swift? So Swift was introduced 10 years ago, a bit more, as a language to develop for the Apple platforms, but also as a general purpose language. And so it's meant to be doing anything from scripting to system programming. And so very soon afterwards, Swift was open sourced. There was a Linux version available. Then after that, the Swift server workgroup was formed so that it would promote using Swift on the server side, so implementing things like REST APIs. And then we have a version of Swift on Windows now. But nothing for embedded until that year. Not entirely true. So there were initiatives like Swift for Arduino and Man Machine and other individual contributors who published stuff. So a big kudos to them for doing the pioneering work. But there was nothing official from Apple. So let's check maybe why that is. And for that, we will compare a mid-level microcontroller, which is an NRF52840, which is, for instance, used in the Apple TV Siri remote control. And we'll compare that with an Apple Watch Series 0, so the first one. And if we look at the processor, we see a single-core 32-bit versus a single-core 64-bit. No big deal. Clock speed, we are at 64 megahertz versus 520 megahertz. So we already see an 8 times difference between those two. In terms of RAM, we're looking at 256 kilobytes versus 512 megabytes. So that's a 2000x difference. And in Flash, 1 megabyte versus 8 gigabytes, so that's 8,000x. And so we see that if you want to bring Swift to this limited environment, we will really need to reduce the runtime overhead, the memory consumption, and the code size, executable code size, sorry. And so embedded Swift is Apple's official answer to that. It is Swift with limitation, so it's a subset of the language, not a dialect. And it basically introduces a compilation mode that will enforce constraint, that will help with the reduction goal I just mentioned. So how does it do this? What are the constraints, basically? Well, it's being deterministic at compile time. So it's removing everything that is dynamic. So no dynamic reflection, no existential types, but as Nick showed this morning, not that big a deal. No generic instantiation at runtime, so generic is still there. Of course, no Objective-C, as there is a runtime, and no dynamic code loading. And so what this means is that we have a minimal runtime library, mostly concerned with memory management. We don't have any metadata on the types. There's no runtime to use it. There's also a reduced Swift standard library. And so, for instance, codable is gone. And it performs aggressive dead code stripping. So only the code that will get executed will be in the final executable. So in practice, it means we have 3 additional flags on the Swift compiler. We define the target, so which platform do we want to compile to? It's cross-compilation. We enable the embedded feature, which to this day is still experimental. And we have the WMO, so whole module optimization flag that would help with the dead code stripping. And as the embedded Swift user manual puts it, it's a compilation mode that would produce an object file, much like a C compiler would do, that would then get linked with the rest of your code. So how does the linking occur? Well, the linking, it's not really, embedded Swift is not really concerned with the linking. It's really the tool chain of your target environment that will do the linking. And what's the output of this? Well, as already told many times during the day, it depends. So let's take a closer look inside of this chip that I was talking about. If you look in the reference manual, you will find a schematic like this, which can be simplified like that. So basically what we see is that there is the microprocessor, a bus, and everything is connected to it. So you have the RAM, the ROM, the IOs, the radios, everything connected to the bus. And what the processor will see is a big region of memory with everything mapped to it. So that's all that matters to him. And at this level, no operating system, no file system, no memory management. And basically, your code and your data must be present at specified location in RAM or in Flash. And when you flip the switch, what the processor does is go to a specific address and start executing what's there. And so we see that we would use a Mac-O or an ELF file, which is really codable code. It wouldn't work, and so we need to transform it so that we can flash it to the device. And the embedded Swift user manual describes the different steps required for embedded development. And indeed, we've seen that there is the building of the Swift source code, which is what embedded Swift is mainly about. And there is the linking and the post-processing that we talked about. OK, enough talking. Let's do some coding. And so for this, I will use the NRF 52800DK, which is basically the same chip I showed, but in a developer kit. So I have button, LEDs, a debug interface, etc. So let's set this up. The first step we would do is install the developer tools for the board that you're targeting, not thinking about Swift at this stage. So that's what I have here. It's for the Nordic boards. It's the NRF Connect SDK, which is based on Zephyr, which is an open source project. But here it comes as a handy extension to Visual Studio Code. And so you can see a UI where I can do different things, like manage my SDKs or create an application. So let's start by testing one of their app. I'm going to create a sample application. I'm going to do Blinky, which is the hello world of embedded, so blinking an LED on and off. And I create this. Normally, you would just run the examples as is, so that you don't introduce any change. What I'm doing is, so you can follow along more easily, I'm changing the LED from an internal one to the external one so you can all see that it will be blinking. Okay, and now I can use the SDK also to create a build configuration. Because the SDK supports many boards, you need to first configure it to use your board, and then I'm adding a file so that it knows about my external LED over there. And then I can click Build. It will launch CMake, which is the tool that they're using, which is like a meta build system, compile everything. And when it's done, I can, with one click, flash. And no, I'm not seeing it, but I suppose you should see a blinking LED anytime soon. Yay! OK, thank you. So now that we've seen that it works with the examples from without thinking about Swift, let's start thinking about Swift and go to the repo published by Apple. So that is their repository, and we see many different examples for many different boards. So depending on the board that you have, we have the ESP32, the Raspberry Pi Pico, ST Microelectronics, and the one I'm using here, NRF. So if we go into this example, we can see, well, the same board, and then Apple telling us install the base SDK, Zephyr, and then make sure you have a recent nightly Swift toolchain. And this is still true to this day, so if you want to do embedded Swift on boards, the SDK shipped with Xcode 16.1 will not work, so you need to go to Apple, the Swift.org website, go to the snapshot, and download the latest main from the branch there. Once you've done that, you can check the README and follow all these instructions. So let's do that. So I'm checking I have indeed installed the latest toolchain, and I'm keeping quite a bit of them so that I can sometimes see if there are regression or not. And then I'm extracting the ID of that toolchain, and I'm setting my environment variable so that I will be using this toolchain. So the next step is launching the build. And again, CMake is interesting. Yeah, there was, really? What is this? Why did I move this? OK. So of course, demo gods are not with me anymore. Let's quickly do something. Sorry. What is this? OK. Apologies. I think we will go to plan B, and I'm very sorry for that. So you only saw part of the demo, and we go back to slides. So we keep time short. So as I was saying, we install the toolchain, and then we can type all the commands from the README, and we get something working on the board. And yeah, that part we saw. We need to export the toolchain to make sure that we use the toolchain we just downloaded. I don't know about you, but to me, typing all those commands is not a really good way to develop. What I want to be able to do is work in an IDE and yeah, have code completion and all that kind of thing. And so that the next step is setting up a proper development environment. And so what I did was use the VS Code extension from the toolchain, add the extension for Swift, and then work in the VS Code. And so there we can set up the environment so that we can stay in the environment and have everything I show you. I can connect to my board, see the console, and I can, with one button, flash everything, build everything, and flash it to the board. And so we'll have the LED flashing, and that's everything with Swift. Once you've done that, I would suggest that when you want to create your own code, you start from the examples done by Apple. And so we can take a look at the code from Apple. And this is the main function. So that's, again, the blinky LED. We have the struct main and the static func main. But then we have things like GPIO pin configure DT and LED 0. What's that? That's not really Swift. Is it? And so if we look in the bridging header, the bridging header is a C header file that will basically expose your C object to Swift. And there we can see that we have the includes for the SDK that we're using, Zephyr, and that we have the declaration of this LED 0, which is a C struct that represents my LED or my pin there. OK, but to me, this doesn't look very Swifty. That's using Swift for glue code to call C. So the one thing we want to do is isolate this C call and encapsulate it in a Swift object, so a Swift struct. So that's what we do. We move the C call into a Swift struct. And we pass it, we have an initializer passing it the LED that we want to control. And in C, it's a pointer to a struct. And so here, it becomes an unsafe pointer to that struct. So that might be some construct that you use less often in Swift. But there are a ton of manual memory management types that you can use to do these kind of things. And with that in place, we can rewrite our main function so that it looks like normal Swift. We instantiate our structure, and we call a function on it. Now, if you look in the NRF Connect SDK, it will tell you that you're not supposed to use a GPIO pin until you checked that the GPIO is ready. So let's do that. We will create an error to capture that possibility, and then in the initializer, we will do the check, throw the error, and so our initializer becomes throwing. And when we try to build this, we get a build error. The Swift compiler is telling us that we're using an existential type. And that is because the throws is the equivalent of throws any error. So that's an existential, that's something that embedded Swift doesn't like. Fortunately, there is an easy fix to that. There is the feature introduced in Swift 6, which is type throws. And so in the throws clause, you specify the error that you're throwing, and that fixes the build issue. By the way, it's really one of the few use cases for type throws, so don't overuse them. We need them because we don't have any existentials embedded Swift, but in regular code, yeah, not really, don't use them everywhere. OK, so far we just ignored basically or didn't do anything with the error that we were throwing. So let's modify the call site so that we do print a message if something goes wrong. And yes, sorry, Daniel, we're back to the caveman age. But that's all we have with embedded Swift, so that's what we'll do. And when you do this, another build error. But this time, it's not the Swift compiler that's telling me quite explicitly what goes wrong. It is the linker that's telling me error code 1. OK, thank you. And this got me into a rabbit hole of trying to understand the whole build system. As I said, CMake, so that was new to me. I had to look that up, try to add some flags, try to get some additional information, understanding the compiler, the linker script, all of that kind of things. And I couldn't find anything wrong. And so one day I said, well, I will look into the repository again. And there was a commit by an Apple engineer, the engineer that did the dub talk on embedded Swift. And I said, well, fix PIC setting. PIC standing for Position Independent Code. And of course, I took that, and it fixed my issue. It compiled fine. If I'm telling you this, no, it's fixed, so you wouldn't have the problem. But I'm showing you this because First, embedded Swift is not only about knowing Swift, it's about everything that goes underneath what's happening there. So you will sometimes need to get a bit lower level. And also, well, I wanted to, I don't know if I would have found anything in a week, a month, whatever, but I would say go to the forums, ask the question. I was a bit stubborn and I wanted to find out myself to really understand, and I had the time, but otherwise, use the forums, that's for there. And with that, we have our blinking LED again, but in Swift. So with that in place, what you do is just keep going and see. So I had the LED encapsulated in a struct. So now I wanted to do a button encapsulated in a struct, and this posed a whole lot of challenges. And I have a couple of blog posts about it if you're interested. And then you grow from there, and you have some projects. Well, let's try again if the demo gods are with us this time. And so what I will do is I will show, hopefully, flash this to the board and see if that works. Nothing wrong here. OK, and this is basically combining all that with, you can see the objects for an LED, a timer, a button, and I'm making now a traffic light thing. So normally, if I press the button, it should go to orange, wait a bit, go to red, and eventually it will go to green. Thank you. And if you look at this source code in the main file, not on the different types there, you see regular Swift. So I'm having a button with a generic, because there's a no generic instantiation at runtime, but there's a generic specialization at compile time. So if it knows what it's doing at compile time, it's happy. I have a trailing closure to do the handling the event. I use enums, I use observation with this did set, et cetera, switch case. So everything you would expect of Swift, you can use there, and this looks like Swift. OK, that. Let's go back to the slide again. So yeah, now let's take a step back, because at some point I showed you the bridging header, and I showed you, well, this is the LED 0, which is a struct that represents my I/O pin to which my LED is connected. But that's a bit of magic. So what's happening behind the scene? Let's take a look again here. And so my LED is connected to a GPIO, so a general purpose input-output. So that's the I/O pin, and we see that this is mapped into memory. And if we look further in the user manual, we see that this board has basically two banks of pins, and it gives you the base address to which it is mapped. Then it will give you a list of registers for the different operations that you can perform on this I/O port. And so let's pretend I have my LED connected to pin 3 of my port 0. And the first thing I want to do is configure that as an output, because often the pin can be input or output. So what I need to do is, well, look up which is port 0, so that's the base address, and then look up the register that will be setting the direction for which the direction of my pin. And then further down in the documentation, I will see that a 0 means an input, a 1 means an output. And so what I need to do is set bit 3 of this address to 1. Easy, let's just do it. So you can do that in plain Swift. So there's everything to read memory, do bitwise operation, write to it. But that's not that easy. So that's, if you're going the direct memory access route, I would suggest using Swift MMIO, which is an open source package that basically allows you to define a Swift model on top of those registers, and then you can just, for instance, flip a Boolean, and that will be somehow mapped to flipping the correct bit at the correct address. So that's making things a lot easier. The other route is to use a hardware abstraction layer on SDK on a real-time operating system, and that's what we've been doing with NRF Connect SDK. And to my knowledge, most of them are C-based, or different based on on the board. So in Espressif, you would be ESP-IDF and FreeRTOS and stuff like that. But they're C-based, and so you would need to use the Swift-C interop to do that. Wouldn't it be good if it was Swift-based? Yeah, but for the moment, it doesn't exist. And so it's a good moment to understand what embedded Swift is and is not, because we talked about what it is, but not what it is not. And so, indeed, the user manual again says that it's not a one-click solution to program every board. You need to have the toolchain of your board to do that. And it's not a hardware abstraction layer or a complete SDK either. So it's the compilation mode, but it allows you to build such things. And so I think that over time, that's what the community will be doing. Either, as I've done here, building wrapper types around the C-based SDK that exists, or maybe building SDK from scratch in Swift, using then memory-mapped I/O, for instance. OK, with that, I hope you have some idea of what embedded Swift is or is not. And so what about this journey? Well, clearly, there were some pain points. To me, at least, there were quite a few new domains that I didn't understand or that I had forgotten. So working with embedded systems, as I said in the beginning, was new to me. So understanding a bit how these boards work, that's outside of Swift. The whole build tool chain, so you're not using Xcode, you're not using Swift Package Manager, at least it depends on the board, but most of the time not. You will often need to talk about CMake and Ninja and stuff like that. You need to understand them in the process of compiling, linking, the linker script. You will need to read C code and sometimes quite complex C macros and function prototypes, and so use Swift-C interop. And you will need to use some less used features of Swift, like everything that's related to manual memory management. The other pain point for me was that things were quite evolving over time. It's getting a bit better, but back at the beginning of spring, or the end of the spring, beginning of summer, there were quite a few hiccups on the road there. And so there is this great post by the Embedded Swift team that explained what is already done, what's in progress, and what will eventually be done. For instance, there are things that they will never do, but there are things that they're thinking about, but it's not yet there, like Swift concurrency. So if it's a bit painful, why do we want to do it and still use Swift? Well, as I showed in the beginning, there are quite a few embedded devices, and they're getting more and more complex. And so traditionally, we've been using C and C++ to work with that. And so the community is eager to find alternatives to C and C++. And so Swift would bring that kind of robustness and predictability that the language, with, for instance, strong type checking, etc., the language provides to the embedded world. I also think that as embedded Swift will get more mature and the community will develop things, we will have the Swift packages to help us, and so that productivity will really increase. Another benefit is, of course, if you're doing multi-platform project where you have a firmware and an iOS app, you can share some code between the two. So is it really used? Well, from Apple, what we know is that it's used in the secure enclave. That's for sure. Besides that, there are links in the embedded Swift examples to community projects that use it. For instance, on the Flipper Zero or the Playdate, there are some people showing example of that. And the Swift for Arduino team has some commercial projects using their tools. And so I would guess that if there are companies wanting to use embedded already now, they will switch or at least evaluate what Apple has to propose as the official answer to this. And then I'm developing a few sample projects. So you've seen the traffic light. In the middle, there is like a reflex board game that I developed also using the same chip. And then, of course, because we can do it, we can do an arc reactor, because yes, Swift does support arc. And so let's do it. We can do it. So that's fun with... Thank you. And so yeah, you can do everything with touch control, so you can have whatever you do. So if you want to scan my contact details, come find me afterwards. I can also control this over Bluetooth and play around with the LEDs and all kind of stuff. No, I've used embedded devices because they're quite fun and they're visual, but embedded Swift can be used in many different situations. And so everything that's below the OS is a good candidate to use embedded Swift. So everything like bootloader and firmwares. The OS itself, so the kernel and all the kernel extension, we could use that. And then in terms of user space, a lot of the Swift tools are written in C and C++ and some of the libraries, etc. And so there's an opportunity to rewrite a few of this in Swift. OK, and WebAssembly, as Steven showed yesterday, would be a candidate to using embedded Swift to reduce the size of the executable there. So I would say just get started. You can pick a board to play with. The ESP32C6 is very useful, or widely used, sorry. Start with their toolchain, make sure that their example work. Then you can move to Swift, download the toolchain, start from the embedded Swift examples, and grow from there. With that, I want to thank you for your attention. I want to thank the organizer for giving me the opportunity to talk here today. And yeah, let's keep in touch. And I try to post every 2 times a month about embedded Swift on the website. So yeah, and as Antoine told yesterday, I will commit to post all the examples by the end of the year. So I have peer pressure to do that. Thank you.
Thank you very much, Eric. So nice with people learning from each other and improving, and yeah, good stuff. We're all in one big family. Yes, we have time for questions. There's many questions. The first one was all the way in the back.
Hi, hello. Thank you for your talk. As an electronic engineer, I appreciate it. I want to ask, what about Arduino programming with Swift? There is something about that, or only generic microcontrollers? Thank you.
Yeah, so for the moment, the Swift for Arduino project exists, which is different from embedded Swift. Embedded Swift doesn't support Arduino so far. There are initiatives to bring that. Basically, the architecture and the processor is not supported. So the 80 Atmel processor, the 80 Tiny, etc., are not yet supported. But there are definitely people who want to get there. So I suppose this will happen in coming months, hopefully.
Good. We had another question from Henrik.
Yeah, I would like to ask, now you had a picture of a Home Assistant. Have you made any devices for that using embedded Swift?
Of home automation?
Yes.
No, yeah. I plan to. So the thing is, I have a ton of ideas of project to do, of course. And it took me much more than expected to have a LED flashing in Swift. So before I could move to a more complex project, but yes, I will. I have an ultrasound device to measure the amount of water left in my water tank, and I want to install that and communicate over a thread to my main system. So that's the next project I will tackle. And then using the same small screen there, I want to replace some of my light switches in the living room with this so I can control everything. So those are my 2 next projects that will be slightly more useful than this. Yeah.
Yes, question down there.
Thank you. Thank you for the talk. I was really excited by seeing that you have multiple Swift files in your project. I've tried Raspberry Pi Pico, which is, I understand, a different world, but I would still be interested in how you managed to have multiple Swift files.
Okay. How much time? Still okay? Okay. So in here, what I did was simply in the, where is it? In the instruction to CMake to compile the main.swift, I added the other files. There is one caveat. If you look closely, I have structs in there. I tried it with classes. It doesn't work. And I don't know why yet. So yeah, that's what I was saying. Sometimes you have really weird things with embedded Swift, and sometimes you find out why in an hour. Sometimes you bump your head against your desk for days and doesn't find anything. So this one, yeah, I'm happy to do it with structs, but with class I haven't found out why it fails. The next step is to look into the object code that is generated and see if there is anything that stands out, but yeah.
And another question.
No,
sorry,
sorry, we'll stop. Yeah, we will move on to the next one.
I just wanted.
Yeah, sorry, no, there was just one.
Okay.
You do it afterwards, sorry. Yeah, but thank you so much for this. And yeah, if you've learned something interesting, maybe post back on Slack or something.
We can
Thank
talk
you.
afterwards.